In this episode, we will talk about data augmentation for real-world multi-hop reasoning with transformers. So transformer models, they're incredibly good at many language tasks, right?
Oh, absolutely. Things like summarizing, translation,
Yeah.
they've really pushed the boundary.
But there's this persistent challenge, this multi-step factual reasoning thing,
Yeah.
especially with real-world facts.
Exactly. It's about connecting the dots.
Yeah.
Like knowing fact A and fact B and using them together to figure out fact C, even if C isn't explicitly written down anywhere.
Right, like your example, Michelle Obama is married to Barack Obama.
Okay.
And Michelle Obama was born in 1964.
Uh-huh.
But the question is about, say, the birth year of Barack Obama's spouse. The model has to link those two separate facts.
Precisely. And that's hard when the knowledge is, spread thin across tons of data.
Yeah.
Transformers can sometimes just memorize what they see.
Rather than actually reasoning or generalizing.
That's the crux of it. They might memorize the training data really well, but fail when they see a new combination of facts that needs that same reasoning pattern.
Which leads us perfectly into this idea of grokking. It's a fascinating term.
It really is. It describes this, somewhat sudden shift you sometimes see in neural networks during training.
Yeah, like the model spends ages just memorizing, performance isn't great on new stuff, and then bam, it suddenly seems to just get it.
Exactly. It transitions to almost perfect generalization, understanding the underlying logic.
But, and this is key, right? Most of the early work on grokking was in very controlled artificial settings, like math problems.
Yes, right. Toy examples, like
Yeah.
modular arithmetic, places where researchers could precisely control everything, especially the ratio between basic facts and facts that needed deduction.
They called that ratio phi, right? The ratio of inferred facts to atomic facts.
Yes, exactly. And they found that when this ratio phi hit a certain point, the network would suddenly switch to generalizing. It was like an internal circuit for that logic formed.
Okay, so this deep dive is about research trying to take that grokking idea out of the lab, basically, and apply it to messy, real-world, factual data.
Tackling that problem of sparse data, the facts are there, but they're too spread out for the model to easily learn the connections.
And they're doing it using data augmentation.
Right. The core idea is, if the real data doesn't have enough multi-step connections, let's artificially add more, boost that ratio of inferred facts to atomic facts.
They're trying to force the model to hit that grokking threshold.
That's the hypothesis, even with complex real-world knowledge.
And here's a really interesting twist. You mentioned this earlier. Sometimes the synthetic data they added wasn't even factually correct.
Yeah, that was a pretty surprising finding. It seems like even incorrect synthetic examples can help.
How does that work? It seems counterintuitive.
The thinking is that it forces the model away from just memorizing specific facts. If some facts are wrong, the model has to rely more on the structure of the relationships, the patterns of how things connect.
So the incorrectness acts almost like a regularizer, pushing it towards learning the general rules of reasoning rather than just the facts themselves.
Exactly. Learn the how, not just the what.
And the results were pretty impressive, weren't they?
Very much so. On the 2 Wiki multihop QA benchmark, that's a standard test for this kind of reasoning, they hit 95 to 100% accuracy.
Wow, that's near perfect. And much better than other methods.
Significantly better, yes, especially considering how tough 2 Wiki multihop QA is. It uses Wikipedia data, requires combining info across different articles or paragraphs.
Like our Obama example, you need multiple steps.
Precisely. So getting those kinds of scores suggests this augmented data approach really helped the model learn to reason much more effectively.
Okay, let's dive into the problem a bit more. The limitations of transformers in multi-hop reasoning. We've touched on it, but why is it so hard for them?
Well, as we said, it's partly the tendency to memorize, especially when the training data doesn't have many examples requiring multiple steps. If you mostly see single facts, you learn to retrieve single facts.
You don't build the machinery for combining them.
Right. You get good accuracy on data you've seen, or very similar patterns, but you fall down on novel combinations. That's the failure to generalize.
And this 2-wiki multi-hop QA dataset is designed specifically to test that, right? That ability to combine facts.
Yes, exactly. It's built from Wikipedia, so it reflects a large, complex knowledge graph. Real entities, ambiguous language sometimes, lots of different relationships. It forces multi-step reasoning.
So linking Michelle as wife of Obama and Michelle born in 1964 is a typical example of what it tests.
A perfect example of a 2-hop reasoning path required by the dataset. It's a good proxy for real-world reasoning challenges.
It's not just finding facts, it's navigating the connections between them.
Precisely. It represents this vast web of knowledge, mirroring the complexity and sometimes the messiness of real-world information. A really solid test bed.
Okay, let's circle back to Grokking itself. You mentioned those early studies on synthetic tasks like modular arithmetic. What did they really show?
They showed this clear phase transition. The models would train for a long time, sometimes getting worse on validation data initially, just memorizing the training set.
Mm-hmm.
But if they kept training, and if that crucial ratio, phi inferred facts over atomic facts, was high enough, suddenly validation accuracy would shoot up.
The generalization kicked in.
Right. It's like the model finally induced the underlying algorithm or rules from the data. They talk about a generalizing circuit forming internally.
A generalizing circuit, like it built its own little logic engine for that specific task.
That's a great way to put it. Instead of just storing answers, it learned how to compute the answers.
And the big challenge with real-world data, like Wikipedia, is that this phi ratio is naturally quite low.
Exactly. Real knowledge graphs are sparse. You have tons of individual atomic facts, but the connections needed for multi-step inferences might be relatively few and far between compared to the number of atomic facts.
So the natural structure of the data doesn't provide enough examples to push the model into that Grokking state.
That's the problem this research tackles head-on. Can we artificially create enough multi-step examples through augmentation to trigger Grokking, even with messy, sparse, real-world knowledge?
Makes sense. To really nail this down, maybe we should quickly define some of these key terms they use. Knowledge graph, atomic facts.
Good idea. So a knowledge graph, KG,
Yeah.
so think of it like a network. You have entities, the nodes, like people, places, things, concepts.
Okay.
Then you have relations, the edges connecting them, like is married to, located, and invented by.
Got it. Nodes and edges.
And the basic building blocks are atomic facts, also called F1 facts. These are simple statements, usually triplets, subject, relation, object, like Michelle Obama, wife of Barack Obama, explicitly stated knowledge.
The ground floor facts.
Exactly. Now, an inference step is just following one relation, moving from one entity to a neighbor. An inference path is a sequence of these steps, following multiple relations.
Like walking along the connections in the graph.
Right. And a simple path is one where there's no ambiguity, no branching choices along the way.
Clear trail.
Now, based on these paths, you get nth order deductions, F to n. These are facts derived from paths of length n. A two-hop deduction, F2, uses a path of length 2.
Like our Obama example. Barack Obama, wife of Michelle Obama, born in 1964. That's derived from two atomic facts.
Precisely. HR1BR2T, derived from HR1B and BR2T. A three-hop, F3, would involve three relations. Maybe something like Obama, President of USA, capital Washington, D.C., located near Potomac River.
Okay, so inferred facts, FI, are basically anything needing more than one step. Anything F2 or higher.
Exactly. FI includes all facts derived within one steps. Crucially, atomic facts, FA or F1, and inferred facts, FI, are separate sets. One is stated, the other is deduced.
And when the model does this deduction internally, without explicit step-by-step prompts, that's implicit reasoning.
Yes, it's relying on those internal circuits formed during training, maybe through grokking. This contrasts with things like chain of thought prompting, where you explicitly ask the model to show its work.
Makes sense. Okay, now this generalization ratio this seems absolutely critical.
It really is. So phi, but with the subscriptor, it's calculated per relation.
Per relation, okay.
Yes. For a specific relation R, it's the number of inferred facts involving that relation divided by the number of atomic facts involving that same relation. So, FIR, FAR.
And the idea is each relation needs its own ratio to be high enough to be grokked.
That's what the evidence suggests. There seems to be a threshold for each relation's FIR, maybe somewhere between 3.6 and 18 for GPT-2 style models, though it's approximate. If a relations ratio is below that, the model probably won't form a reliable generalizing circuit for it.
Wow, okay. So a generalizable knowledge base is one where all relations meet this threshold, which they call FIDGE.
Right. If all relations have Cherev G, the whole KB is potentially generalizable via Grokking. If only some relations meet it, it's partially generalizable.
And they also distinguish between in-distribution ID and out-of-distribution inferred facts. What's the difference there?
Both are facts the model didn't see directly in training. But ID inferred facts are new combinations of atomic facts the model did see. It knows the pieces, just not this specific arrangement.
Like knowing ingredients A, B, C, and being asked to make a new dish A, B, C, even if you only ever saw A, B, and B, C separately.
That's a great analogy. Ode inferred facts, though, are tougher. They might use atomic facts the model knows, but the reasoning path itself, the sequence of relations needed, is one the model never encountered during training.
Ah, so it's not just combining known pieces in a new way, it's following a completely novel route through the knowledge graph.
Exactly. ODE is the much stronger test of generalization. Can the model apply its learned relational understanding to entirely new inference patterns?
That distinction feels crucial for really knowing if the model learned to reason or just memorized a lot of paths.
Absolutely. That sudden jump in ODE accuracy is often considered the hallmark of true grokking. It shows the model has gone beyond memorizing training examples.
Okay, with those definitions locked in, let's get back to the data augmentation strategy itself. How did they actually do it?
So the goal was to boost that phi ratio, more inferred facts per atomic fact. They used a two-stage process. First, augment the 2-wiki multihop QA dataset with synthetic knowledge. Second, train a transformer on this richer dataset for a long time to train trigger grokking.
And they looked at both structured data, the clean subject relation object triplets, and unstructured data, the full paragraphs.
Yes, and within those, they focused on two task types, comparison and composition.
Comparison being like, are these two things the same in some way? And composition being chain these relations together?
Exactly. Same country is
Yeah.
comparison. Director of the sequel to Film X is composition.
So for the comparison task, how did they generate the extra data?
They started with a small set of real atomic facts, mostly about geographic locations like city, country, triplets, or short paragraphs.
Okay.
Then they used a large language model, LLM, to generate more atomic facts about new locations, keeping the same format. So just expanding the base knowledge.
Making the map bigger,
Yeah.
essentially.
Right. Then, to create the inferred comparison facts, they systematically paired up distinct location facts. If fact 1 says Avignon's in France, and fact 2 says the Louvre is in France.
They generate the question, are Avignon and the Louvre in the same country?
Precisely. By doing this systematically across their expanded set of atomic facts, they massively increased the number of inferred comparison examples.
And they got that feed ratio up significantly.
Hugely. They went from about 120 atomic and 60 inferred facts initially to about 1,000 atomic and 8,000 inferred facts. That pushed FIG up to 8, well above that Grokking threshold range.
Wow, 8,000 inferred from 1,000 atomic. That's a big boost. What about the compositional task? That seems harder.
It is more complex. For composition, they started with some atomic and inferred facts, making sure the answer wasn't directly stated. Then, they used an LLM parser to turn the text into a graph structure, entities, and relations.
Okay, mapping it out.
Then they enriched that graph, adding some new plausible atomic edges, carefully avoiding cycles. And then they sampled multi-hop paths length 2 or 3 from this denser graph.
So finding new potential reasoning chains within the augmented graph.
Exactly. Each path, like obj1, rel obj2, rel j2 represents a new inferred fact. Then they used another LLM to turn that structured path back into a natural language question, like the ones in 2-wiki multihop QA.
So LLMs were used both to parse the initial data and to generate the final questions from the synthetic paths.
Yes, leveraging LLMs at multiple stages. For composition, this process got them to about 800 atomic facts and 5,000 inferred facts, boosting FIG-E to 6.25. Again, aiming to get past that critical threshold.
It's really clever using LLMs as tools to generate the right kind of data to train other models better. And this ties back to the surprising finding about incorrect data, right?
Yes, because even if some of the LM-generated facts or paths weren't 100% accurate according to the real world, the sheer volume of these multi-hop structures seemed to be what mattered for pushing the model towards learning the reasoning patterns.
The structure over strict factuality, at least for triggering the generalization mechanism, fascinating.
It suggests focusing on the relational logic might be key.
So they did all this augmentation, boosted the phi ratios, then they trained their transformer. What happened? What were the results on 2-wiki multihop QA?
They used an 8-layer GPT-2 style model. First, the baseline, trained on the original structured comparison data without augmentation.
Okay.
It got 100% training accuracy, perfect memorization. But crucially, 0 jump in ODE accuracy, even with long training.
Confirming the original low phi ratio, around 0.5, wasn't enough for Grokking.
Exactly. But then, on the augmented structured comparison data,
The one with fig of 8.
yes, they saw a clear, significant late-phase jump in ODE accuracy, just what you'd expect if Grokking was happening. The model learned to generalize comparisons.
Success. What about the augmented structured compositional data? The fig was lower there, 6.25.
Right. There, the results were mixed. They got near-perfect ID accuracy, so it memorized the compositional patterns it saw, but ODE accuracy stayed low. No big jump.
So even with augmentation, generalizing complex multi-step chains is harder than simpler comparisons.
It seems so. The complexity of the reasoning path itself matters. Maybe a phi of 6.25 wasn't high enough for these harder tasks. Or maybe compositional reasoning just needs more or different kinds of examples.
Interesting. And what about the unstructured tasks using the full paragraphs?
Training was slower to converge on ID data there, which makes sense. Parsing paragraphs is harder than triplets. And they only saw modest ode gains,
Why only modest?
likely the noise and ambiguity in natural language. Even with augmentation, the effective phi ratio might be lower because the model struggles to extract the clean relations consistently from the text. It makes generalization harder.
So structure helps. Clean triplets make it easier to learn the relations and trigger grokking than messy paragraphs.
That seems to be the case, though they still saw improvements in ID accuracy on unstructured, showing the augmentation wasn't useless, just less effective for ode generalization there.
How did their grokked GPT-2 compare to bigger, newer models like GPT-4o?
On the structured data set, their smaller, specially trained model was very competitive. On the comparison task, it actually outperformed models like GPT-4o and O1 Mini, hitting almost 100% OOD accuracy.
Wow. A smaller model, trained this specific way, beat the giants.
On that specific structured task, yes. Now, defining ID versus O for pre-trained giants is tricky. They've seen so much data. But it highlights that targeted training for grokking can be really powerful, maybe more efficient than just scaling up for certain reasoning tasks.
That's a huge point. Smart data and training might beat brute force scale sometimes.
It certainly suggests that avenue is worth exploring much more.
Did they look at specific examples? Like what kinds of questions did it get right after augmentation that it likely wouldn't have before? And where did it still fail?
They did. Success cases included complex 2 or 3 hop queries, things like which painter was born in the same city as the founder of Company X, or the simpler, do City A and City B share the same country?
Hmm.
Stuff requiring connecting facts.
The kind of things it failed on without the augmentation.
Exactly. The failures often happen with relations that were still rare, even after augmentation,
Yeah.
or ambiguity, same name for different people or places.
Ah, so data sparsity for specific relations or entities can still be a problem.
Yes, and also inconsistencies in the data itself. They mentioned issues where the expected answer format changed, like needing French sometimes and France other times, and it struggled more with entities like lakes, rivers, airports, where the base data was probably thinner to begin with.
So the augmentation helps immensely, but it doesn't magically fix underlying data quality issues or extreme sparsity for niche topics.
Precisely. The overall takeaway was boosting phi with synthetic data is key for grokking-based multi-hop QA, but complexity matters. Unstructured text is harder, and data quality still limits things. But that jump for simpler queries really shows the potential.
Definitely, it's a promising direction. What did the researchers themselves see as the main limitations and next steps?
Well, one big thing is testing this on more diverse reasoning tasks. Longer chains, different domains beyond Wikipedia, maybe temporal reasoning, how does it handle time?
Right, pushing the boundaries.
And also deeper analysis. How exactly do these generalizing circuits form? They mentioned needing more work on quantifying factual drift. Does the inaccurate synthetic data subtly harm the model's overall factual accuracy? And using mechanistic interpretability to really dissect the model's internal workings during grokking.
That factual drift point seems critical. Given the finding about inaccurate data helping, you wouldn't want the model becoming a confident liar.
Absolutely not, especially in high-stakes areas like medicine or finance. So they suggested future work on constraint-based augmentation ways to boost fail while guaranteeing factual accuracy, perhaps.
What else?
Broader scope questions. Does grokking work like this outside Wikipedia facts? For common sense, moral reasoning. And then there's the practical side. Feasibility. Training for grokking can take a long time, computationally expensive.
Yeah, that's a big hurdle for large models.
So they mentioned exploring things like scaling laws, maybe faster training techniques like curriculum learning, or using pre-trained models as a starting point, hoping their existing knowledge accelerates the grokking process.
Lots of open questions, but a really intriguing path forward.
Definitely, it's a solid foundation for thinking about how to build models that don't just retrieve information, but actually understand and reason with it.
Okay, so wrapping up the steam dive, the big takeaway seems to be that smart data augmentation, specifically aiming to increase that ratio of multi-hop inferred facts to single-hop atomic facts, can actually trigger Grokking-like generalization for reasoning in language models.
Yes, and the really provocative finding is that even imperfect, non-factual synthetic data can contribute positively to this, apparently, by forcing the model to learn the underlying relational structure instead of just memorizing surface facts.
Which opens doors for potentially more robust, maybe even more interpretable, knowledge-intensive NLP systems down the line.
Huge potential. But, as we discussed, it's not a silver bullet. Full generalization, especially for complex relations or in messy text, is still a major challenge.
So maybe the final thought for everyone listening is this. How do we build future AI systems that develop these grokking abilities more naturally, more efficiently, moving beyond massive memorization to genuine understanding and reasoning? What new kinds of data or training methods or even fundamentally different architectures might get us there faster while ensuring the reasoning is actually reliable and factually grounded?
That's the multi-billion-dollar question, isn't it? How do we get from knowing that something is true to understanding why? This research offers one intriguing piece of that puzzle.